Hi, so now I'm redoing some of my previous videos, like this one, the single degree of freedom oscillator, the mass spring damper kind of system. And that's because Blender 3.6 now has a simulation zone, which is a little different way of doing it than what I did before. I was using this ping pong kind of technique. It's kind of a hack in the geometry nodes kind of setup. So here we go. This is just single degree of freedom oscillator, as I said, and the displacement of that oscillator, it's described in terms of displacement, which is this u as a function of t, time, and you can look this up in a lot of different books out there, but it's e to the minus zeta omega nt, and that is multiplied by u naught cosine omega d t plus u naught dot plus zeta omega u naught divided by omega d times sine omega dt. And the zeta is damping ratio, which is damping, the ratio of damping to the critical damping. And then omega n is the natural frequency, which is basically, if it's a mass spring system, it's the square root of k over m. And then omega d is the damped natural frequency, which is the natural frequency times the square root of 1 minus zeta squared. And so now let's get into it. We open up a geometry node setup, and I'm kind of keeping the timeline there so I can turn it on and off. And what we want to do is do an instance on points, and I'm putting an icosphere there. And I started with the cube, but what I want to do is actually go into edit mode and then merge all these into a single point, so that I only have one point right now. So I add a simulations zone and then connect the geometry inputs, and there I have the icosphere. So first I'm going to set up a bunch of values for inputs, and these are going to be the values that are the variables in this equation: the zeta, omega n, u naught dot, and also time eventually. So I'm putting these in, and then those are inputs into the simulation zone. So I'm going into the node for the simulation zone and changing the names just so I have them all straight. So first I'm going to work on that omega d, which is the square root of zeta, which is square root of 1 minus zeta squared times omega n. So here I take zeta to the power of 2, take 1 and subtract that value from it, and then take the square root and then multiply it here by omega n, the natural frequency. And so I'm going to describe this as omega d, and there it is. And so we're just slowly building up this equation that I wrote in the 3D viewport. And I want a time to go into this, so I'm going to have this is time, and I'm going to set it to 0, and that's going to go into the simulation as well. So I take this time, and then I want to add this delta time and then feed that into the output time, and that means that time is going to loop through, so it's going to increment by that delta time each iteration of this simulation. So now I'm going to take zeta and omega n and then multiply it by u naught, and then I'm going to add u naught dot to that, and then divide it by this omega d that we calculated before, so we have that factor that's on the sine term. And then I'm going to take this time, and this is a node wrangler hack, a node wrangler command. If you shift right mouse slash across one of these noodles, then you can create a node there, and then you can move that node around, so it makes things a little bit cleaner. It's going to be a little messy here, but we're going to try to get it clean. So then I'm dividing that quantity that I just calculated by the omega d, so I have that full factor on the sine term. Multiply omega dt by t, and then do a sine and cosine function of that, and then I'm going to multiply the sine by what we calculated. That's that term in front of it, and then the cosine needs to be multiplied by that u naught. So there, I'm setting up that part of it. So then I just set up the addition of those two terms, and then the exponent, I'm going to go ahead and start setting that up. So in the power, in this base term, if you type E, it'll give you that that factor, the 2.7, whatever it is. And so we're gonna multiply this by the u naught times the cosine term, and then the sine times its term, and then we'll have this whole equation for u as a function of t. And then once we have that calculated, we're going to feed that into the position of the geometry with a set position node. And let's see, why is this not working? Well, let's see what I'm going to do. I'm going to take that time and the add. I'm going to add my own value to it. I think what I need to do is feed these other terms, the zeta, the omega n, the u naught, the du dt naught, feed those in, and look, there it goes. Now we have something oscillating there. So what I'm doing here is taking the omega n that I want in hertz, but in order to calculate, to use it in these equations, I need to turn it into radians. So I'm typing tau in for the value that I multiply it by, and that's going to multiply it by 2 pi. And so now that I have the icosphere kind of oscillating around, what I want to do is kind of step it up a little and I put a shade smooth onto it, and then these are the values that I used for zeta, u naught, du naught dt, and then the time is 0. And here I'm taking the time and then multiplying it by 1 over 24 because the default animation number of frames per second is 24 in Blender. Here in the output, what I did is I grabbed a spiral and I have a value that's being read into it, which is the displacement value that u as a function of t. And then I take the spiral and I changed it so that it's a constant diameter, and adjusted the number of rotations until I liked it. And then I put a set position in there, and the set position kind of adjusts it down because I want where it starts to stay still and the other end of it to kind of oscillate with the system. And so I took that as a set position, and then did a curve to mesh, and on the curve to mesh I'm using a curve circle to create that sort of spring-like diameter on that curve that defines it. Did a transformation there, and then set some materials, and I think the transformation I really didn't do anything there. So then I set some materials. One's kind of a shiny red ball, and then the other's kind of metallic spring. And then I set it up to run, and you can see it oscillates. There's the equation there. And that's kind of it. It's a little easier now with the simulation zone. So there you go. If you like this type of video, click like or subscribe, and I'll see you in the next one.